Hello, everybody, and welcome to Dot to Dot. Today, we're going to talk about the summer and the winter solstice and how it may be related to Oak Island, and more in particular, how it's related to Nolans Cross. Now, it's been proposed by Brian Farrow, Oak Island theorist, that the summer solstice sunrise lines up with the axis of Nolans Cross. And you know what? That's somewhat true, but there's a little more to it, and it's really amazing. We're also going to look at the winter solstice and what it shows us, which is really, truly amazing. And it is especially related to the Zena-Halper map and the vault theory. So before we get started with looking at Google Earth, I'm going to go over a couple of terms that you're going to need to know. And that is the elevation, or the altitude of the sun, and it is the angle from the horizon to the sun. Now here it's a simple picture, but actually the elevation of the sun starts at the very top of when the sun breaks the horizon at the top. And the other term we're going to need to know is the azimuth. In other words, the angle. The angle is to true north, and it's measured in 360 degrees, and this is showing where the sun's position is on the horizon as far as its compass heading, basically. So I got a couple of pictures here. Here's a picture of basically 0 degrees elevation of where the sun is just topping the horizon. And here is when the sun is pretty much full, where the full disk is shown. And usually this happens, it depends on the latitude, between 2 to 5 minutes after the initial sunrise. And this is a full disk. And this comes into play on Oak Island, and I'll show you in a minute. But we need to know these couple of things. And the information that I'm getting all this, and this is, I'll leave a link in the description. This is the NOAA solar calculator right here. And it's really cool. This is their newest solar calculator. You can move this around and put it wherever you want. You can put it right here on Oak Island. It automatically puts in the latitude and the longitude. It also adjusts the time to notice it's 3 hours to daylight savings time, and there's a lot of neat things you can do with this. And we'll be using this I've used this in my calculations here. So let's go to Google Earth, and right now I have positioned, and I'll explain this. This red line here is just east-west, and the green lines are what are called the apparent sunrise. And this is apparent sunrise is just, it's a term that means the sun is basically observed at the horizon, but actually it's below the horizon. But, you know, it's something that it's more scientific than it is for our purposes, which is the observed sun. When is it being observed? And it will be an apparent sunrise, but this is not really going to really matter to us. The pink is the azimuth, or the pink is the axis of Nolans Cross. And we have also, this is the winter solstice sunrise right here. And this is the 45-degree angle mentioned in the formula. This is going to come into play. And we have the sunset at the winter solstice. It does not align with Nolans Cross. So the summer sunset is up here, and it sort of goes close to cone C, but not really. So really all we're talking about here is the summer solstice sunrise and the winter solstice sunrise. Now, according to Brian Farrow, these are observed at cone A. So cone A is the most eastern portion of Nolans Cross. It's the top of the cross. Now, when we look at the sunrise, or we look at the the axis of Nolans Cross, we will find the elevation here. Here's cone A. The elevation is way above the horizon. So in other words, the sun is going to have to rise up in the sky to this point above 23 feet in order to be observed at cone A. So the fact that the sunrise is not in the axis, the apparent sunrise is not at the axis of Nolans Cross, we're going to find that when it does hit the axis of Nolans Cross, it will be just observable. It will be observable at cone A, and it's going to be a full disk, which is really interesting. So here is the terrain of cone A is right here. Now I have the distance set from 23 feet, the center of the obstacle at 23 feet, and standing behind cone A about 10 feet, which is 395 feet. So here's sea level. And when we do the calculation by putting a line here, this is where the sun is going to rise to our observable point. So we put a line there, and we measure that distance, and we get a distance of 2.3 degrees to 16 feet. And then if we go another 7 feet, it is another degree. Now you might say, well, this guy is not viewing it from the ground. He may be 6 feet tall. He's still going to have to observe it at after it goes past the 23-foot rise here. So when you do that math, it comes out to 3.3 degrees. Now the sun has a diameter of about 1/2 of a degree. And here's something from, I think, Wikipedia that shows that it's pretty much known that the diameter of the sun disk is 1/2 a degree. So therefore, when the sun rises on the summer solstice, it will be visible. It will be visible above this 23-foot hill right here at a full disk at 3.8 degrees. So when we go to the solar calculator and we put in the time to adjust it to where it's 3.8 degrees, when it gets up to 3.8 degrees, we find that the azimuth is at 60.03. So pretty close. And these things, they go by quickly. So this is really, if you want to go to perfectly 60 degrees, this will be, I think it's 2.877, and it's only a matter of a couple of seconds. Like, I think it was like 11 seconds to go back. So this happens very quickly. And I would say that this is pretty much an affirmation that the sunrise over that 23-foot hill, when it's a full disk, will be at 60 degrees, which is in line with Nolans Cross, the axis of Nolans Cross. So now when we go to the winter solstice, okay, the winter solstice has a huge hill to go over, at least at the sunrise. So the sunrise at cone A, is clearly not visible at the apparent sunrise. So when is it visible? So you have to move forward in time, and you come to this line. And this line is basically at 135 degrees. And the azimuth, or the elevation, will be 8.3 degrees in angle. Now, let me prove that to you. We have the elevation of, oh, it's not opening. Okay, there we go. So this is the cut of the elevation of cone A. Now notice here's the 30 feet. It actually goes to 30 feet when you go to 135 degree angle. When you go to 135, it is 30 feet here. You still can't see it. And the obstacle that we have to overcome is right here, which is 26 feet. So if we stand at 178 feet, which is 10 feet behind cone A, and we do the math again, we get 5.1 to 16 feet and 3.2 to the top of 26 feet, which gives us a angle elevation of 8.3 degrees. So basically at cone A, when the sun is just breaking, not like before where it's a full disk, when it's just breaking, when you see the first light come over this hill of the sun, the angle will be at 135 degrees. And that is the angle of the 45-degree angle from La Formula that goes to the Oak entrance and through La Hampe. This has to do with the Zena-Halpern map because it is the north arrow. When the Zena-Halpern map is oriented, it is the arrow, the north arrow, that creates the 45 degrees that goes down there. So it's very interesting that this winter solstice is 135 degrees at 8.3 degrees in elevation, where it just starts to be visible to cone A. So that's the winter and the summer sunrise solstices. And I think I already said it, the sunset on the winter solstice does not line up with Nolans Cross. And the summer solstice sunset doesn't really go anywhere either. So pretty interesting. Brian Farrow is definitely correct, I think, in saying that the summer solstice lines up with Nolans Cross axis. But I found it even more interesting that from cone A, where it is visible on the winter solstice sunrise, is in line with the 45-degree angle from La Formula, and it is discovered through the Zena-Halpern map. Well, thanks for watching. Please like and subscribe, and I'll talk to you later.